All right, today we are cracking a case that's been hiding in plain sight right inside one of the most important materials on the planet, steel. You see, for ages, we've known how to make steel incredibly tough, but we didn't know exactly why it worked on the atomic level. So let's dive into this little detective story.
So here's the thing, it's a real puzzle. If you take hot steel and cool it down super fast, that's called quenching, you make it incredibly hard. But, and this is a big but, that hardness makes it brittle, like shatter like glass brittle. The fix is a process called tempering, where you gently heat it back up. It's like magic, trading that brittleness for toughness. But how?
And that was the million-dollar question. Scientists and engineers knew the recipe worked, but what the atoms were actually doing down there, this tiny little dance happening on an unbelievably small scale, well, it was a complete black box. They had some good theories, sure, but no way to actually prove them.
To solve this thing, we first need to meet our cast of characters, the key players in this atomic drama.
Okay, so the steel we're looking at is a low alloy steel. Iron, of course, is the backbone of the whole thing, but the real star, the one that makes it all happen, is carbon. It's this tiny, super nimble atom that zips around between the bigger iron atoms, and that's what makes the structure hard. Then we've got silicon and manganese in the mix. You can think of them as the supporting cast, influencing the final outcome. So here's the process. You quench the steel, and that locks all the atoms into this really hard but super stressed out structure called martensite. Then you temper it. You add just enough heat to let those atoms relax a little and rearrange themselves. The whole point is to form a new, super hard compound called cementite. That's what gives the steel its legendary toughness. The mystery was all about how that cementite actually forms. And this, right here, brings us to the two main suspects in our investigation. Two competing ideas for what's really going on when you temper steel. Okay, I love this because it's so easy to picture. Think of the carbon atoms as these little zippy motorbikes. And then you've got the much bigger silicon and manganese atoms, which are like big, slow-moving trucks. So theory number one, para-equilibrium, says the whole process is so fast that only the carbon motorbikes have time to move and form that cementite. The trucks? They're basically just frozen in traffic. Theory number two, local equilibrium, says no, the process is slow enough for everyone to move. The trucks actually have time to get to their designated parking spots, with silicon getting pushed out and manganese getting pulled into that new cementite structure. Scientists actually drew up blueprints for what these two theories would look like if you could see them. And here they are. So for the para-equilibrium theory, that's the motorbike's only model. See how the line for manganese, or Mn, is just completely flat? That means it hasn't moved an inch. For the other theory, you see these big spikes and dips. That means those trucks have moved. The problem was, for decades, nobody could actually see the atoms to know which blueprint was the right one. Yeah, for the longest time, seeing this was impossible. But then a new piece of tech came along that could finally peek inside the steel and watch the action unfold. It's called Atom Probe Field Ion Microscopy, or APFIM for short. And honestly, it's almost like magic. What it does is it takes a needle-sharp sample of the material and literally plucks atoms off, one by one, and identifies them. It creates this perfect, atom-by-atom 3D map of what's inside. For our mystery, this was the ultimate surveillance camera. And this is what it sees. This is not a simulation. This is a real picture from inside the steel. Every one of those bright dots is an atom, or maybe a small clump of atoms glowing on the detector. And those dark patches the arrows are pointing to, that's the cementite we've been talking about. For the very first time, scientists could see the crime scene with perfect clarity. So the researchers set up the experiment. They tempered the steel for a little while, pointed their atom probe at it, and what did they find? So the first test was on steel that was tempered at 350 degrees Celsius for just 30 minutes. We're talking about the very beginning of the process where those first crucial changes are happening. And boom, this right here is the breakthrough. On the left, you've got that theoretical blueprint for para-equilibrium. Remember? Flat lines for silicon and manganese. And on the right, that's the actual real-world data from the atom probe. It's a perfect match. The carbon level just plummets as you cross into the cementite, but silicon and manganese, dead flat. I mean, the evidence was just undeniable. Right at the beginning of the tempering process, it's only the fast motorbikes, the carbon, that are moving.
The big trucks, silicon and manganese, are completely left behind, so case closed, right? The para-equilibrium theory wins. Well, not quite. The best detective stories always have a twist, don't they? So the researchers started wondering, what if 30 minutes just isn't enough time? What happens if you let those atomic trucks sit in the heat for hours and hours and hours? So they ran the experiment again. Look here on the left, that's our data from 30 minutes. You see those flat lines for silicon and manganese. But on the right, this is after tempering the same steel for 180 hours. Look really close. You see how the lines for Psi and Mn aren't flat anymore? They're starting to slope. The slow-moving trucks have finally started to move. Silicon's getting pushed out of the cementite, and manganese is getting pulled in. And here it is, the big reveal, the stunning conclusion to our mystery. It wasn't one theory versus the other. They were both right. They were just describing different parts of the story. Tempering isn't just one thing. It's a two-stage process that happens over time.
Okay, so we've solved an old scientific puzzle. Pretty cool. But what does this mean for you and me? Why is knowing about this two-stage atomic dance so important in the real world?
This table just sums it all up perfectly. In stage 1, the early stage, it's all about carbon. It moves fast, forms that strengthening cementite, while everything else just stays put. That's para-equilibrium. Then, if you keep the heat on, you enter the extended stage. The other elements slowly start to move to where they're most stable. That's called partitioning. The number 2, that's the secret. Realizing that tempering isn't one process, but two distinct phases, driven by completely different atomic movements, well, that was the absolute game changer.
And this is why it really matters. Because we understand that these two stages exist, engineers can now control them. They can design heat treatments that stop after stage 1 for one set of properties, or let it go deep into stage 2 for another. This lets them create custom steels with unbelievable precision, perfectly balancing strength and toughness for everything from car parts to skyscrapers to rocket engines. Just as the original researchers put it, what they found shows how important kinetic constraints are. That's just a really scientific way of saying that sometimes speed is everything. That massive difference in speed between the carbon motorbikes and the silicon trucks, well, that's the secret sauce that controls the whole process. So, a mystery that was decades old, solved. It just makes you wonder, doesn't it? As you look at all the stuff around you, the metal, the plastic, the glass, what other incredible atomic ballets are unfolding right under our noses, just hiding secrets, waiting for the right tool and the right detectives to finally bring them into the light? Thanks for joining me.